So this chapter's title was Sampling and the Normal Distribution. So it's now in 1104 that we start to look at the normal distribution. You would have previously possibly called this a symmetrical curve. So the shape, it will be quite familiar to you. You would have seen me frequently draw a curve or a graph where we've got frequency and score, and you'd see me draw it like this. The only difference now is we rarely actually put this vertical axis in. However, we keep this shape, and yes, we have a score axis. So you can see, hopefully you can see that here. Now, there's quite a few assumptions about this sort of distribution or graph. And we will always have this shape. And the number one assumption, I guess, is that the average will be nicely in the middle. So yes, it has a symmetrical shape and the average is in the middle. It's called a bell-shaped curve, and you'll see it referred to as bell-shaped. I guess in some ways we could see this as a bell, or like a big Christmas bell. And is called a normal curve. There are many things that occur in real life that actually, if we graph them, would give us this sort of distribution or spread, and things like blood pressure. So if we took quite a variation in ages and male, female, etc., and graphed blood pressures, we'd see that blood pressure is, some people have quite low, the majority have this average blood pressure, and some people, very few people, have a very high blood pressure. And heights, if we surveyed enough people within a group, say of 18-year-old females, if we got a big enough group and we graphed their height, you would see that that also would create a normal distribution. Now, not only is the mean here in the middle, we also assume that the median and the mode are also in the middle score or the middle value of the normal distribution. We know that standard deviation measures spread, and there are some really interesting features about the standard deviation and this normal curve. So from the average, if we mark off one standard deviation, now the size of the standard deviation, because it measures spread, very much depends on the overall shape of the curve. So a curve like this, we know, or you'll know very soon, that its standard deviation would probably be quite small compared to, say, this graph, whose normal distribution looks, the distribution looks like that, the mean being here, and we know that we're going to cover 3 standard deviations to get here to the very top. 1, 2, 3. So one standard deviation is actually that distance, and we know that because standard deviation measures spread. We can see that these results are very spread out. Whereas with this distribution, although it's normal, it's got quite a small standard deviation, because by the time we get to the end, we have covered 1, 2, 3 standard deviations. Now again, there's something really interesting that if we look even closer at 1 standard deviation above the mean and we take the same distance below the mean. So if this, for example, was 60 and the standard deviation was 10 units, the next deviation would take us up to 70 and down to 50. If we look in this range from score 50 to 70 of a normal distribution, we find that 68% of the population lies within that range of scores from 50 to 70. So it says there 68% of the scores lies within 1 standard deviation. Now, when we say 1 standard deviation, we mean from 1 standard deviation below the mean up to 1 standard deviation above the mean. So really it spans across a total of 2 standard deviations. But it's 1 standard deviation either side of the mean. If we extend out then to say 2 standard deviations, so we've come down 2 and up another one, so it takes us up to result 80 and brings us down to result 40. Now we can see that we're covering quite a large number of the results altogether, and in fact if we go 2 standard deviations below and 2 above, which I guess in essence covers 4 standard deviations in total, but we say within 2 standard deviations of the mean, so 2 below, 2 above, 95% of the results lie within that spread or that range. And then finally, we've got 99.7, maybe go a different colour, say black. 99.7 of results, and that is extremely close to 100% of the scores lie within the 3 standard deviations of the mean. So down 3 standard deviations, which would take us down to 30 and up to 90. In that range of scores from 30 to 90, we can expect 99.7% of the scores to lie. So if your score was actually outside that, then you are in an extremely high percentage bracket of the scores, and not too many of the population actually get up above that 3rd standard deviation, nor below the 3rd standard deviation. So here's a much nicer, more spread out, much more accurately drawn normal distribution showing those percentages. So rather than talk about 1 standard deviation, we're going to say 1 Z-score above, 2 Z-scores above, 3, 4 and so on. We rarely talk about 4 and we rarely talk about -4. Now, what do these numbers represent? Remember it said that this was 68%. So if we halve it, then we're talking just about this region here from the mean. So this Z-score of 0 means we're spot on. There's no difference between this result and the mean. It's on 0. 1 Z-score up would be 1 standard deviation away. In this category, we've got half of 68, and half of 68 is 34. So it says that 34% of the scores lie within this range from the mean to 1 standard deviation. Now, because the mean changes from distribution to distribution, and so does the standard deviation, it does make more sense to talk about Z-scores than actual results. So we'll keep it very standard in terms of we're talking about the mean here, we're talking 1 standard deviation, 2 standard deviations, and so on. So we've got, again, 34% on the other side. You might be wondering where the 13.5% came in. Well, remember that if we span 2 standard deviations, then we were up to 95%. So how much more was added on to get to 95 from the previous 68? So take that away and we will then have both this region and this region added together here in order to get up to 95. So what's this? 7 and 8 and 27. So the two dotted regions together represent 27%, and we've got to split them evenly. Half that above and half below. Half of that is this 13.5%. And so that's where that number comes from. Then to go to 3 standard deviations, remember it was 3 standard deviations was this 99.7%. Now, how much then was added on in this region? Well, remember we had our 95% previously, and when we subtract, we'll get 4.7, but that 4.7% is split over 2 equal amounts. So if we divide that by 2, then we get 2.31, which is a 5. 2.35, which, whoops, if I had better uncover that a bit, is the 3.5%. Then outside that, above 3 standard deviations, is this 0.15%. Very, very small percentage of the population. Where did that come from? Well, we say that the total graph represents 100%. Our 3 standard deviations was this 99.7%. So if we do the subtraction, we have to borrow 1 and we get 0.3%. And that has to be divided up into 2, and we get 0.15, which is the percentage that the arrow is indicating to here, and that would be this region in here. So it's below 3 standard deviations, and likewise up here above 3 standard deviations. 0.15 of the population is very small. I'm going to stop the video there and I'll talk about the examples later.